Hi ho! Welcome to Constant Velocity Motion Screencast to help you further understand what we did in the beginning of the semester for physics class. Yay! Alright, so constant velocity motion. Here we have a little picture that I drew from my notebook because I don't have any cool um, icons and stuff like that to help me draw it out like the smartboard does. So pretty much here, constant velocity is illustrated, let's say, by a car traveling on a road. Let's say that it's frictionless, so that we don't have to deal with annoying friction. So we have our motion maps here to help us understand how the velocity doesn't change, how the velocity remains constant. So here, as the car continues to travel down the road, we see that our velocity vectors, our velocity arrows, they don't change. They are constant. They stay the same length, and that is because our velocity isn't changing. And here we have acceleration equaling 0, because when our velocity doesn't change, when our velocity is constant, acceleration equals 0. And therefore, we have our total net force equaling 0, because net force and acceleration correspond with one another. So, to elaborate on this, we can illustrate what's happening with this car here in some graphs. And so we have our position graph, we have our velocity graph, and we have our acceleration graph. Automatically, we know that acceleration is 0, so therefore there's nothing here drawn here. Acceleration is on the 0 line. There's no acceleration. And we have a constant velocity, and that's represented with a horizontal line, a constant slope. And pretty much we here have the area of the velocity versus time graph equals the displacement, or the change in position. So if you look up here, the slope of this graph, the position time graph, is our velocity. The slope of the velocity graph is our acceleration, and the area of our velocity versus time graph is our displacement, which is here, as you can see. So from this, we can create all types of equations. So with the first graph, our position versus time graph, we look at it and we see that the x final, the very top of this slope, equals the slope, which is the velocity versus time, plus the initial position. Almost like the slope-intercept form, y equals mx plus b. That's what this graph gives us. This graph gives us an equation of x equals vt plus x naught. So final position equals the velocity times the time plus the initial position. So we have the displacement, or the change in position, equaling velocity. Because when you subtract x final from x naught from both sides, you get the change in x equaling the velocity multiplied by the time. And that's how all these equations correspond with one another. Especially, and you can get these equations from the graph. And these are all vector equations. And a vector shows both magnitude and direction, while a scalar only shows magnitude. So I guess, for instance, a vector would be position and velocity and acceleration and all that, and then a scalar would be time and distance. That those would the scalars are the numbers that pretty much scale the vectors. When you have vt, because velocity is a vector quantity, time is what changes that vector quantity. V multiplied by t, t being the scalar, time being the scalar, you change your velocity. So that's just the relationship between that, and that's why and that's why these are, why these are vector equations. And if we continue on with this, we see something else, like the example I gave on my summary. We here have a plane traveling from the loading dock to the runway at 2 miles every minute. We'll say on a frictionless surface. That's kind of unlikely, but yeah. So it's just the same thing. Our velocity arrows don't change, just representing that we have a constant velocity. Therefore, we have zero acceleration. Therefore, the total net force is 0 because acceleration is 0. And to continue, there are some common misconceptions that I wanted to bring up about constant velocity, and things that just need to be made clear so that everybody understands what velocity is and when it isn't. So as you can see right here, velocity is not a force. Velocity is a vector. Velocity is the change in position over the change in time. That is what velocity is. And it is a vector that gives you both magnitude and direction. It tells you where you are relative to where you began and in what direction. So you have negative 2 meters per second. That tells you that at 1 second you are 2 meters to the left of your original position. That's what velocity is. It's not a force. It doesn't cause motion, but it is motion. Velocity doesn't cause motion, but it is motion. That's one way to say it. And there's another misconception that says if velocity is 0, then acceleration must be 0. That's completely untrue. For instance, take when you throw a ball in the air. When you throw a ball in the air, let's see if we can exemplify this here. When you throw a ball in the air, your velocity graph will look like this, I believe. Oh, excuse me. That's not pretty. Let's try that again. So when you throw a ball in the air, your velocity graph will look something like this. And when that happens, okay, flip it, whatever. But when that happens, you have a tangent line at the very peak of it. Let's just say that this is a perfect one. I'm sorry, it doesn't look perfect, but let's just say that it is for a second. Let's say that it's perfect. It's a perfect upside down parabola. When that happens, your velocity is 0, but technically your acceleration is still changing from, let's say, from positive to negative. When you throw that ball up in the air, your acceleration is negative, and sorry, so yes, your acceleration is negative because your velocity is decreasing. And then at the very peak of it, your velocity becomes 0, but your acceleration is still changing from negative to positive. Alright, so therefore, acceleration does not have to be 0 when your velocity is 0, because acceleration can be changing. So that is a common misconception that needed to be addressed, because that can definitely ruin a person's whole idea of constant velocity and, really screw them up in physics. So that was something else that needed to be addressed. And that's pretty much it for velocity. Velocity is a vector, not a force. It does not constitute acceleration being 0 if velocity is 0. That doesn't work. It always gives you magnitude and direction. Therefore, it's not a scalar, so don't get that confused. Yeah, and that's pretty much all the common misconceptions about velocity. And so, to continue on, there's some other things I want to address, like the model for constant velocity. Here I stated the model as being for every increase in time an object's position increases or decreases the same amount of time. Like for every 5 meters, so if your velocity is 5 meters per second, for every second your object's position increases 5 meters. So that's how velocity works. And so, pretty much this model is basically the same as or similar to our constant acceleration model. If you think about it like that, it's saying constant acceleration is saying for every second your velocity increases a specific amount. Saying that for every second, for 5 meters per second squared, for every second your velocity increases 5 meters per second. So for every second your velocity goes from 5 to 10 to 15, and it's the same thing with velocity. Just instead of it being velocity increasing, it's position increasing, and so therefore for every second you're increasing 5 meters instead of 5 meters per second. So we're saying for every second you're increasing from 5 meters to 10 meters to 15 meters, and that's one relationship that I can find with the model of constant velocity. So now here is a problem that I think would be pretty helpful just to understand the basics of constant velocity. So we've got a block sliding to the right with a mass of 10 kilograms. That's not really important. What's important really is that it travels at a constant velocity of, again, 5 meters per second. And now this problem is asking us how far has it traveled in 10 seconds, and what is its velocity at t equals 10 seconds. So let's see. We've got 5 meters per second multiplied by 10 seconds. Seconds over 1. So seconds cancels out, 5 times 10 equals 50, and the last unit you're left with is meters. So we know that 50 meters is how far it travels in 10 seconds. What is its velocity at t equals 10? Well, because it travels at constant velocity, we know that its velocity never changes. So at t equals 10, its velocity is still 5 meters per second. So that's just a little problem to help you understand, you know, constant velocity. Constant velocity never changes. So therefore, acceleration is 0. And therefore, our velocity doesn't increase, doesn't decrease, it doesn't change anything. It just gives us the direction and the magnitude of our object. So we know that at 10 seconds, our velocity is 5 meters per second, and that this object has traveled 50 meters. That's cool. And so just to answer some of the following questions, like for instance, implications and applications, well, what is the implication of this model that we have studied in a greater context? Well, the implication of this model is that um, lots of things travel with a constant velocity and a constant acceleration, but we'll get to acceleration later. But for a constant velocity, a lot of things travel in constant velocity at times. Like say, for instance, a car traveling down a horizontal street at 30 miles per hour for, I don't know, let's say for 2 miles, and then when the street starts to curve, the car releases its foot from the accelerator, and then you decrease in velocity, and then you change direction and all that stuff. But for that specific amount of time before the road changed, that was constant velocity. We didn't speed up, we didn't slow down, we were staying at a constant rate for I believe I said 2 miles. And so that is the implication of this model. The implications of this model is that things travel with a constant velocity. I don't know how to say that better, except to say that objects with a constant velocity never change the type of direction, type of motion that they're doing. When it's constant, it's always staying the same. So that's the implications of that. We've already provided specific applications with this model, and then we just did a sample problem. And so some of the societal and historical implications of this model, and the other fields that this model could probably relate to, could be, let's say, historically, constant velocity is how a lot of things move. Like I said before, it's always been that way since the beginning of time. I can never think of a ball rolling across a floor and then automatically sorry, I can't think of a ball rolling across an ice surface and then automatically slowing down. That doesn't make any sense. Um, so I can't think of that because there's no friction going the opposite way, and so on a horizontal surface, I feel like maybe that ball could have constant velocity. Um, so And I mean that's sort of, these are sort of like broad, difficult questions, but that's how I feel like it applies. It definitely does apply, and it's definitely integrated into society, into history, because this is the way it's been. These are like the laws of motion. These are kinematics. These are laws of motion. Um, you know, it objects move with either constant velocity or constant acceleration. Um, and maybe a few other ways of motion, but for the most part, constant velocity and constant acceleration. And so that's how it always works, and that's how it implies in history. Um, and a current event or something else that relates to me and how I can apply this model is, when I'm driving down the street every day, or I'm walking to school every day, and I'm walking on a flat surface to one of the classrooms. Let's say I'm walking to F6, and I'm walking on the sidewalk underneath the covers, underneath the awnings. I'm walking with a constant velocity. I'm not speeding up. I'm not slowing down. I'm just at a same steady pace, and that's something that and that's one way I can look at my everyday life and how this applies to it. This is science. My life is science. Science applies to my life, and constant velocity is in everything I do. So, thank you.